All right. Thank you very much for the introduction, Jill. Thanks to all of you for participating in the webinar. My role really is to bring science in support of the work that Chuck and John are doing. And it's been an honor and a real privilege to work with them. They're top-notch. And I don't think we'd be where we are without the knowledge and experience that they've brought to bear. I want to give you a glimpse of...
Likewise, it's all built on Greg's science.
So we're taking a look at California's urban forests top-down and bottom-up, statewide inventory of urban forest carbon stocks, climate action reserves, revision to the urban forest protocol, and some new research testing climate-ready tree species. So that's the agenda. First, I think it's important to note that actually only 5% of California is defined as urbanized area with population over 2,500. But that's 8,000 square miles and 95% of the state's population. So we are an urban state, and we have a challenge in terms of mapping the tree canopy throughout the state, identifying potential tree planting sites, and we're using U4 plots, urban FIA plots. We now have about 50 municipal forest inventories that are all providing on-the-ground data that we're combining with remote sensing, and we're doing this assessment in conjunction with our partners at UC Davis and CAL FIRE. So we have some initial results for street trees from the 41 street tree inventories, and you can see a diagram of where those cities are located. We found about 10.7 million trees. That's about one tree for every 3 people. We found that there were about 83 trees per street mile, which is actually a lower density of trees than was found in 1992, the last similar survey where they found over 100 trees per street mile. So we've got some work to do to catch up there. Given this one tree per 3 people, and the street tree density is about 39% of full stocking, where full stocking would be a tree on each side of the street at every 50 feet on center. 39% full stocking means we have about 27 million vacant sites, so there's room for planting. And if you think of that street tree resource as a form of infrastructure similar to our roads and our water system, the asset value of that is about $37 billion, $3,400 per tree, and over $1,000 per capita. So it's a really valuable part of our urban infrastructure. We are examining the distribution of species throughout the state. We have 5 different climate zones because we have different species mixes in each climate zone. This shows importance values for the top species in the Northern California coast, with the London plane tree accounting for about 23% of the total importance. And importance is defined as not just the number of trees, but also their size in terms of leaf area and canopy. And these are outputs from running these inventories throughout tree streets. So ideally, we would not want any species to be more than 10%, but you can see sweet gum, magnolia, and London plane are a little on the high side. So that's not a very resilient street tree population. In Southern California, we have the native California sycamore at 11%, but there's a little more even distribution of importance among the different species, which makes it a little less vulnerable. The value of annual benefits from these 10.7 million trees is over $1 billion. That's about $110 per tree and $33 per capita. Property value and other kind of intangible benefits make up the bulk of that benefit, followed by energy, stormwater, runoff reduction, carbon storage, and air quality benefits. And here you can see how the value of annual benefits per tree vary as a function of climate zone. And so we can see anywhere from $80 to $150 per year per tree. The environmental benefits themselves accounting for about $20 per year per tree. We're using remote sensing to classify urban tree canopy around the state, and actually we're getting at 1 meter resolution 2012 NAEP imagery that has been classified by Earth Define at 90+% accuracy. So we will have the classified urban tree canopy for all the urban areas in the state. We're also purchasing land use data from DataQuick, so we'll be overlaying that and having tree canopy by land use to map the vacant tree sites, estimate the benefits from the existing tree canopy, establish tree canopy targets, and monetize the benefits associated with increasing canopy to those targeted levels. And we'll be using field plots to develop transfer functions that we then apply to the tree canopy data. The transfer functions are derived from the U4 and FIA plot data where, for example, we'll calculate the tons of CO2 stored per hectare of urban tree canopy. And we do that by taking these field plots. Here you see 3 trees. We'll measure those in the field, identify the species, determine the DBH and the height of each tree, calculate the carbon stored, and come up with the amount of carbon stored per unit tree canopy for this plot. And then we'll sum that and calculate the average for all the residential plots. And in the example here, the residential transfer function is 50 metric tons per hectare of tree canopy. And you can see an image of tree canopy that's been classified. So in this image, there's about 1/4 of an acre of urban tree canopy. And applying that transfer function, we can calculate 12.5 tons of CO2 stored in the tree canopy in that image. So that's the way we kind of scale up from the plot data to the tree canopy statewide. The second topic is the revision to the Climate Action Reserve's Urban Forest Protocol. Climate Action Reserve is kind of a clearinghouse for carbon credits, and they have very high standards in terms of the quality of the credits that they register and then go for sale on the voluntary market. And the first protocol for urban forest planting projects was developed in 2008. It was revised in 2010. Santa Monica was the only city that was trying to do a tree planting project, and there were a bunch of issues associated with that, which we discussed at a workshop that was held in 2012. And from that came the idea of trying to streamline planting projects, and a new revised protocol, I believe, does that. It simplifies the calculation process, and I think will reduce the cost of initiating and maintaining these projects and reporting and verification. There is a new type of project that we have a protocol developed for, which is called an urban forest management project, and it addresses one of the limitations in that it includes all of the trees in the community or in the project area, not just planted trees. And by doing that, we vastly increase the potential amount of carbon that can be credited. It uses the field plots and the urban tree canopy and the transfer function approach. So there's potential to really reduce the cost, because one of the problems with the planting projects was the cost of tracking each planting site over a 100-year period of time. Now we can just use sampling and tree canopy data to do that. So we're hoping that this will reduce the costs and make these projects more attractive. This is the URL for the Climate Action Reserve and the protocols. The information from the 2012 workshop is available on the American Forest website, Urban Forest and Carbon Markets, and this is the URL where you can download the presentations and learn more about that. In June, the Climate Action Reserve Board of Directors approved the revised protocol. So one question we're asking ourselves is, how will urban forests adapt to climate change? You've probably heard we're in the midst of a 3-year drought. And so the first question really is, what is our urban forest going to be exposed to? Temperature-wise, We know temperatures by mid-century are expected to be 4 or 5 degrees Fahrenheit warmer than they are at present. Rainfall is going to probably be less in Southern California, but there may be slightly more rainfall in Northern California. We may have higher winds associated with extreme storm events. So then the question is, well, how will different species that are most important in our urban forest react to the exposure and stress that they experience from this changing climate, and what is their potential to adapt to the exposure that they experience? And of course, this is going to occur over long time periods, but at very fine scales because of the variability in the microclimates within our cities and within our state. So we've got about $250,000 to assess the climate resilience of the trees in our urban forests and begin answering the question, what should we be planting, what should we not be planting, to make our forests more climate resilient. So we're developing a scoring system that we're applying to the existing trees in the urban forest from both municipal inventory and the plot data. It incorporates scoring of different risk factors for each species, and from that we develop recommendations on whether to continue planting or stop planting or plant more of these tree species. We're also going to try to identify promising species that may not be planted in a region or may be planted in very small numbers and have seen to be successful, but we really haven't tested them very well. So we're going to be evaluating the most promising cultivars, and we have an experimental design that makes use of trees planted side by side of each of the cultivars in UC Cooperative Extension field plots around the state with the same species planted in parks that are nearby that have much more variable conditions in terms of soils and climate and management. And I think we're going to be doing that in 5 different climate zones, and we're going to be monitoring those trees over about a 20-year period of time to assess their performance, and then we'll be every year issuing a report and letting people know how these tree cultivars are performing. And these are just some of the factors that we're incorporating into our risk factor analysis. Habitat specificity with the idea that species that have a very narrow range of tolerance are going to be more vulnerable than species that have a wide range of tolerance to different light exposures, soil moisture, and soil texture, for example. The physiology of trees in terms of their tolerance to heat and drought, salinity as we moved into more recycled water and wind tolerance, and their vulnerability to pests and potential to become an invasive species. So I've spent a lot of my work speaking about the value of trees in terms of carbon stored and the economic monetary value, but I realize more and more that people connect with trees on an emotional level, and oftentimes it's with the tree that they planted and cared for, the tree in front of their home. And so to me, kind of the issue is how do we get people to see that connection between the tree that they've connected to in front of their home and their entire urban forest, of which it's a small part. So I've got this verse I found. A tree in front of my house is a word. The trees on my street are a sentence. The trees in my neighborhood are a paragraph. And all the trees in my community are a story. This is a story that tells us about our relationship to nature in the past and the present. We're the ones that are authoring the next chapter, and our challenge is to reveal the connections between my tree and my forest. So I think this kind of segues into the future of California's urban forest, which really relies on recognizing the link between the individual trees and the larger community forest, and beginning to really protect and expand our tree canopy throughout the state. So thank you.